let's consider solid elements. These were not widely used even as recently as 10 years ago because of the difficulty in making the mesh and debugging the mesh. I don't think the problems were so theoretical as they were just practical. But today, solid elements are widely used. Every code has good solid elements. And in passing through the working areas of automated analysis on the way to the studio here, I noticed several people building solid element models of suspension components. We'll talk a little bit about the theory, and of course it's basically the three-dimensional theory of elasticity that governs. We'll discuss the hexa element and the penta element. Then I'd like to get into some of the specialty topics dealing with subsets of global displacements here in the way that degrees of freedom are reduced during problem solution, and then to show the different kinds of constraints that can be applied, to discuss multi-point constraints and then their application as rigid elements. This will be done pretty much through the viewpoint of the MSc Nastran code, just to give some specific examples of the so-called rigid elements. At the end, we'll have a problem session. The solid element is characterized by its shape and by its material. The shape is very important because the elements don't have reference lengths and moments of inertia and areas as do many of the other elements. One of the simplest elements is a four-noded tetrahedron, which is a four-sided pyramidal element. But it turns out to be too simple. We'll discuss it later and find that the displacement field is linear, which is too crude an approximation for structures. It still is used a bit in heat conduction and in fluid mechanics. The 10-noded tetra shown below is actually perhaps the wave of the future because of automatic mesh generators. The tetra element is a lot easier to generate than the hexahedron element that we'll discuss in a minute. Now the wedge element is a five-sided element. It can take a variable node form shown below, such as a penta element in the Nastran series. It has 6 to 15 nodes. The hexahedron is probably the workhorse today, either the 8-noded version or this more complicated 8 to 20-noded version. Bruce Irons came out with the isoperimetric formulation many years ago, and since then many commercial codes have used that formulation for an 8 to 20-noded hexahedron. And of course this is an isoperimetric element and is numerically integrated. Solid elements are constructed using the three-dimensional theory of elasticity. So that means that the basic mappings in the three-dimensional theory are, again, the heart of the element. In this case, it's possible to carry rather general material properties, such as this general anisotropy that's shown. There can be as many as 21 constants in general. The mappings from nodal to internal or field displacement are the same as before with a shape function n. It's possible instead, however, to use the displacement function approach with the FEA matrix and the H matrix. Orthotropic materials are being used more and more in terms of laminates. Here's the simplification that one obtains when you have a general orthotropic material. In this case, there are only 9 elastic constants. Wood itself pretty much is orthotropic because of the fiber direction and then the transverse direction, various crystals and laminates. Many times materials such as extruded polyethylene that I'm interested in for high altitude balloons has an orthotropic nature because of the way it's made. It's extruded through a die that gives it a machine direction and then a transverse direction in the plane, as well as a thickness direction, all of which can have different properties. The material law then simplifies further for isotropic materials, such that you only have two material coefficients now, Young's modulus and Poisson's ratio. The strain displacement law used for solid elements is the general three-dimensional elastic law. And here we use the engineering definition for strain, which is the sum of the two derivatives in each case. The first solid element that we'll consider will be the constant strain tetrahedron. And this is a bit of a generalization of the original Turner triangle. There are four faces and four nodes, and one can assume a displacement function form such as this then, where each of the three displacement fields is a linear polynomial. It's a complete linear polynomial, giving a total of 4 degrees of freedom per component of displacement. So in total you have 12 degrees of freedom and 12 generalized coordinates. So this is a consistent theory. We can use the basic law that we have for stiffness, shown here, and which inherently considers the geometric part of the problem and then the material part. And the biggest problem here then would be to integrate over the volume that's enclosed. Likewise, we integrate for equivalent nodal loads, and these could be volumetric, or could be surface, or could be line loads. Probably the volumetric load would be gravity or an acceleration field, and surface loads would probably be pressures. Now there's an interesting mathematical sidelight here, and that is that you can use what are called natural coordinates to do this integration. In the case of a solid, you'd use volume coordinates. Now these are a set of normalized coordinates. There are 4 of them, but only 3 independent after applying this normalization, that they must add up to unity. And what these really are is the fractional volume of the tetrahedron that's developed from the point in question and then extending away from the reference node. And so in the case shown with the red lines, if we would heavily outline this tetrahedron now, made up from those lines that are far away from node 1, and then cross-hatch this a bit to show that this is a volume, then that fractional volume would be perhaps 3/10 of the total. Then you'd have to calculate the other fractional volumes as well, and they would add up to unity. Now this is kind of a curiosity because nowadays we mostly would integrate numerically, but it's fascinating to see that there is such a set of coordinates called natural coordinates, and they exist also in 2 dimensions and even in 1 dimension. So you can have an area coordinate or even a natural coordinate on a line. Now I'm discussing this tetrahedral element mostly for historical reasons, because the 4-noded tetrahedron has pretty poor properties with respect to stress. When you have constant stress over the volume of an element, this really can affect the model of your stress field and give quite a stair-step approach to the smoothly varying function. So it acts again as an inclusion in a stress field, locking the stress through the volume of the element, much as the Turner triangle did in an area sense. The most widely used element today for solid modeling is the hexahedron. Now this can come in 2 versions. You can have an 8-noded or a 20-noded version. The body has 6 faces The original 8-noded version is sometimes called a brick, and then irons came up with the 8 to 20-noded version. I have used it somewhat as a transition element by having somewhere in between 8 and 20 nodes, but I would say most often it's used purely as a 20-noded element. The isoparametric formulation is a standard approach using numerical integration. There are some tricks involved. You have to have enough integration points in the interior of the element to avoid so-called zero energy deformation modes. Now I'll have a figure on that next. But in other words, you don't want the position of your integration points to allow the body to move in some spurious deformation pattern. Another trick is that you should be able to recover the shear stresses that are appropriate to a thin body such as a shell. McNeil was quite a pioneer on that, and he has moved the Gauss points around in the solid Hexa element to try to improve the shear response of that element. And then we've mentioned Bruce Irons' 20-noded isoparametric element. Zero energy modes are those types of deformation in an elastic body which by chance do not cause strain energy at the sample points or the Gauss points. This is a mistake in the element formulation in a sense, because either the element has too few sample points or perhaps they're placed at the wrong spots. As an academic example, we could show this brick element above, and its sides might move in such a trapezoidal shape such that there would be very little strain across this horizontal line. If you used only one integration point at the center of the element, you would get a deceptive value of strain energy, deceptively low. And if you stacked up several of those side by side, shown on the right, and put this loading on it, you might get this exaggerated shearing deformation. A second kind, which actually occurs more in practice, is the hourglass mode. This sometimes shows up in nonlinear problems as an instability, where the solution is being done iteratively. In other words, the structural problem is solved over and over, and the body senses that there are certain patterns of deflection it can take that will not cause strain energy. So it gradually moves over into that deformation pattern, and that would be considered an instability in the solution. I've seen this at national meetings where authors are bothered badly by the hourglass behavior. It could happen again, say, where you had this solid element and perhaps a parabolic element whose sides could move with these parabolas shown, both top and bottom. And then you might get the idea that there's no net straining in the horizontal direction here and here, nor is there vertical strain along these other axes. And then if by chance your Gauss points were centered at those intersections, you'd get an abnormally low value of strain energy there. So this is a problem for element developers to face. Now let's discuss the Hexa element. The 8-noded version, sometimes called a brick, even when it's not straight-sided, would be mapped onto the double unit cube shown on the right. You might then use a 2 by 2 by 2 array of Gauss points for the integration. It's been found that this element sometimes is stiff, and it's better to evaluate shear strain at special shear points, which are different from the Gauss points. This is a way that the 8-noded Hexa element is handled in the MSc Nastran code. I feel a little bit sheepish as an instructor at this point because I cannot show the viewer a good, honest stiffness matrix for a solid element. These are numerically integrated, and they only are created in the mind of the computer for a short time and then discarded. One time, a professor friend of mine challenged me, and we were discussing something about solid elements, and he said, well, show me a stiffness matrix. And I felt like a wimp professor because I couldn't. So you'll have to go on the fact that these are created numerically, and you can read them out from the commercial codes by asking nicely. Usually it would be a pretty involved array of numbers, which would be horrifying. Even for one of these 20 noted elements you see, you would have a 60 by 60 stiffness matrix. Well, let's think about this 9 to 20 noted element, and I'm going to describe again the way it's been implemented in the MSc Nastran program, where a 3 by 3 by 3 array of Gauss points is used. These are the red points in this solid. And then the shearing strains are calculated on a 2 by 2 by 2 array, shown in green, and then they're extrapolated out to the Gauss points using the isoperimetric shape functions. This helps correct then for the nature of the over stiffness of the element. The previous reduced integration on the shearing strain energy was due to Richard McNeil of the McNeil-Schwindler Corporation. And he did that in an effort to better model thin shell theory as you squash these solid elements down flat. The element that we've discussed most here is the MSc Nastran Hexa element, and it can have anisotropy, heat transfer, and differential stiffness, which is the type of behavior that leads to elastic buckling. It's quite an interesting capability, and you can, for instance, show surface buckling waves in solids, or even overall buckling in the sense of an Euler column modeled by solids. That's beyond the scope of our current lectures, though. The stresses in any solid element have to be referred to a coordinate system. The default in the MSc Nastran code is the element coordinate system. I much prefer to use the basic coordinates, because then you know your x, y, z directions in all of the different elements. When modeling a body with hexas, you often get caught in a corner in some awkward spot where you need to save your mesh by using a penta. And this is, of course, a 5-sided body. And so in each of the codes there is such a so-called wedge element that is a companion to the hexagonal element. In the MSc Nastran codes, they use isoperimetric formulation. They map the original physical shape onto a unit right triangular prism. And then they have two integration schemes, whether you're using the linear element or the one with more mid-side nodes. Again, there's some worry about the behavior of the penta as you smash it flat into a plate. And indeed, if you do that, there are preferred directions here that the x and y directions in the plane of the plate should be such that you get a triangular plate element such as this. Now, the 6-noded element in Nastran, in MSc Nastran, uses the 6 Gauss points with only 3 special points for transverse shear strain. Then for the more general element, there are 9 Gauss points with only 6 shear points, and they are trying to accurately describe the shear that is in the thin direction, you might say, of the plate to recover the plate-like behavior shown here. That pretty much covers the theory that I wanted to discuss on the solid element. Now let's think about constraints that are needed in models of structures, and these come up quite a bit, and in fact they've been formalized in some of the codes to act as if they are rigid bodies. So it's kind of a natural extension of what we've been doing, where rather than elastic three-dimensional bodies, we're going to speak in a minute about rigid three-dimensional bodies. But at the outset, places where you use constraints in general are often cases where you have reflective planes. And for instance, on this particular model here, I once got involved with the residual stress problem. We invented a hole drilling method where you relieved the stress, which put a harmonic pattern around the periphery of the hole. Then there was, in fact, one reflective plane here and with symmetric loading, and then one reflective plane here with anti-symmetric loading. So those conditions on the cut edge, if you choose then to model only a segment of that body, you see, would be symmetric conditions on the horizontal line and anti-symmetric on the 45-degree inclined line. And those are actually single point constraints involved, and we discussed those a bit earlier. Another case would be that of the generalized plane strain, perhaps a propane tank here that's under internal pressure, and you'd like to isolate some portion of it, so you bring that to the side. The interesting thing is that if you do not resolve the loads on the end cap and you only draw this as your free body diagram, you don't get a very good answer. One way to handle this is to make one of the boundaries fixed, since one reflective boundary could be so fixed and without loss of generality, and then to allow the other boundary to translate in a way that it would bear the amount of unresolved force on this far cap that would have to be present. As you know, the stresses in the body should be PR over 2T in the axial direction for a thin cylinder, and then PR over T in the hoop direction. So in order to get that right, you have to use such a trick and put this on rollers, let's say. Another place where constraints are used is in cyclic symmetry, where one will solve one segment of a body, such as this rotor system shown here. You might solve only a quarter of that body, and then on the cut boundaries, you need to put a repetitive or a periodic boundary condition relating perhaps the displacements at one such node to those of its partner on the other cut boundary. And that would require multi-point constraints. And now we're getting a little closer to our topic here of how we have to learn to tie points together to make a body behave in some overall global fashion. We already did that here a bit on this rolling end cap on this propane tank. I'd like to review the way constraints are handled in the Nastran series of codes. I think it's very instructive, and it's often not discussed in textbooks. This is a way of reducing a problem based on partitioning. And a person would start out with a model that would have a certain number of global degrees of freedom. These would include all of the physical coordinates at the grid points, plus any artificially introduced coordinates. Sometimes there are scalar points and other measures of behavior. Then one would remove a certain set of coordinates that are not needed because they can be related through multi-point constraints to the remaining set of degrees of freedom, which are called the n set. So we have this split then between the u sub m and the u sub n set. Then at that point you can apply single point constraints here and remove a certain set of points that perhaps on reflective planes or fixed boundaries will further reduce the problem, and this u sub s for single point constraint. In some problems, there are degrees of freedom that are omitted. This comes up more in dynamics, actually, with a static condensation process, but it can happen in statics too. It happens in cyclic symmetry is about the only serious case for that. But that would reduce your degrees of freedom further to the analysis set of degrees of freedom. And then, if need be, if you have to remove rigid body molds, that would be a further reduction, and you would be left ultimately with the use of L set. Sometimes people think of it as the leftover set or the left set. To study the so-called rigid body elements, one needs to learn how to tie the degrees of freedom of a rigid body together so that the body acts as a total rigid system. This requires a concept of a multi-point constraint, which by definition does just that. It relates the degrees of freedom in a body, even degrees of freedom at different grid points. So the multi-point constraint concept has to do with a linear homogeneous equation. It's just an algebraic relation between the degrees of freedom in question, and there are coefficients a sub j out front. Typically, the first degree of freedom mentioned in this equation will be eliminated in terms of the other degrees of freedom. Occasionally a person will need a non-homogeneous constraint, that is, a non-zero term on the right side, and what I've done in the past is to create a scalar point and then constrain it to have some non-zero value and then put it into such an MPC. And this was done in controlling the overall rigid body motion of a slide and a transfer press. My intent has been to keep this lecture series code independent as much as possible. You know that one exception has been the use of commercial codes in the laboratory sessions, and that really was necessary. In the case of illustrating rigid elements, I'm going to do the same and use the MSC Nastran code as the example. The ideas are general, and other commercial codes have their own versions of these rigid elements. In the case of a line element and a rigid bar element, you would have a line element extending from node point A to node point B. Such a body in general could have 12 degrees of freedom. It could have 6 at each node. Now, there are 6 rigid body modes in this, so really you'd like to end up by constraining 6 degrees of freedom to depend on the other 6, such that they are the remaining independent degrees of freedom. One way I like to set up my R-bar elements is just to let one end of the element control the entire deflection pattern. So you let the 3 translations and the 3 rotations, say at the left end, control the entire rigid body. Then the right end degrees of freedom will have to be slaves in some sense to the left. Now this will take an intricate set of multi-point constraints because the relation between those degrees of freedom is not trivial. People who've done this say it's a lot of work and painful. A common application used to be the gap between the middle surfaces of 2 plates that had been welded together. Now, in general, though, you could allow an arbitrary pattern of 6 coordinates to control the other 6. Now, I shouldn't say arbitrary. I should say that there are many, it's a non-unique pattern. There are many combinations that could do it, but there are a lot of wrong ways to do it. That's why it's very safe to just let one end control the other end, because you don't run into that non-uniqueness in that case. What can happen is you can over-constrain some of the rigid body behavior and not control some of the other rigid body modes. The way this is implemented in MSc Nastran is with the R-bar name for the element with its own element identification number, perhaps 17. You'll have the grid point at the A end and the grid point at the B end, say 21 and 22. And then the degrees of freedom that are going to be the master degrees of freedom, in other words, they will be in what's called the N set, which survives, are the CNA set at the left end and the CNB at the right. Now, I'm going to illustrate that all the leftmost degrees of freedom at this end are going to control the rigid body. Then I don't put any such degrees of freedom in the field above at the right end. The program can figure out then which are the M set of degrees of freedom. They would be the complement of these. For instance, it then would be logical that all 6 degrees of freedom at the B end would have to fall into the M set and be eliminated.